So I'm going to start by explaining filtration, just using nephron. Um, so the idea is that blood is coming in and then we're leaving. We create a capillary bed before we leave, right? Um, and in this Bowman's capsule right here, the glomerular capsule, we're filtering the blood. And blood is filtered based on a few things. One is size. So larger things, it's harder for them to be filtered because basically, like the idea is there's this membrane um that makes up the filtration membrane. And it's like if you were to put your hands together, like not like completely so that your fingers are, I wish I was on camera right now, so that your fingers are overlapping, but like if they were like not overlapping. So they were like filling the gaps of each other, right? And then you were like kind of squeeze like a water balloon or something. It's like if that stuff were to go through, right? So the size affects filtration. The second thing is charge. So there are proteins in the membrane that make it so that negative charges really don't like to pass through the membrane. So we don't let big things with a negative charge pass through. So like small things with a negative charge like um bicarb or like fluoride, those things do pass through, like that's okay, but big things they don't. And then the other thing is pressure. So if we have a really low pressure, we're going to filter less because we're not pushing on the membrane as much. But if we have a higher pressure, then it's easier to filter. Um, and a lot of things are what we call freely filtered, so they're filtered at like the same rate as water. And this includes sodium, chloride. Chloride does not have a positive charge. Chloride, potassium, glucose, amino acids, um, the list goes on. But they are freely filtered. So they have a TFP ratio of 1 at the glomerular capsule. Now this changes as we go down the proximal tubule, which is this part right here. It's the proximal tubule. Their TFP will change as we go down the proximal tubule because they get reabsorbed, which is coming back into the blood at a different rate than water does, unless it's the sodium. Then they're sodium and water are just buddies. They just stay the same all the time, pretty much. Um, Now, so to affect the pressure and filtration, this is kind of going out of order of the prompt. Sorry, that's probably going to be confusing. But um, we regulate blood flow to the glomerulus. So if we have, I'm just going to simplify this. Um, that's our nephron now, and this is our arterial. And this side right here is the afferent arterial. This side right here is the efferent arterial. Just to simplify it and make it a little bit easier to like comprehend what's going on and so that I can explain without being confused. Um, so if we have a glomerular pressure that's too low, if we decrease glomerular pressure, we are going to decrease something called GFR. And GFR stands for glomerular filtration rate. And basically it's just the rate that of filtration, and it just is really related to pressure because as we push blood through like a faster rate or like with more velocity, we're pushing on that membrane more. So we're going to increase the amount of stuff that gets through the membrane or the amount of stuff that's filtered. So if our glomerular pressure, or we actually call it the hydrostatic pressure of the glomerular glomerular capsule, there we go. But I'm just gonna call it glomerular pressure because it's easier. If that decreases, our body is going to automatically dilate the afferent arterial, I mean. And it does this because if we make it bigger, we're allowing more blood flow into the glomerular capsule, right? So if we're allowing more blood flow, so we increase blood flow here, there's more blood flow here as well, right? Which will increase that pressure because we're increasing the volume and they have that relationship. Another way that we can increase the pressure is by constricting this artery. So if we make this artery smaller, the arterial smaller, then this arterial will kind of back up the blood into the glomerular capsule and we'll have a greater glomerular filtration rate. Um, and this is regulated using, um, well, two mechanisms actually. This one is regulated using, it's called tubuloglomerular feedback. So basically, it's like we have receptors in our tubules in our kidneys that tell us, hey, we're not getting enough of the things that we need, so we need you to dilate so that we get more. And then this one is regulated using the renin angiotensin aldosterone system. And that one is one that we've talked about before, but just like as a reminder, we start with renin, and renin goes through a bunch of these intermediates, and then it becomes angiotensin 2, right? Renin goes to aldosterone. Aldosterone is converted using the ACE, or sorry, renin converts aldosterone to angiotensin 1. Angiotensin 1 is converted to angiotensinogen. And then angiotensinogen is converted to angiotensin 2 using the ACE enzyme in the lungs. And then angiotensin 2 does a few things to help increase blood pressure, to help this system right here, one of which is constricting the efferent arterial. Another one is like increasing thirst. We also release ADH through this. Um, Here, I'll just write them down. So we increase thirst to increase constriction, efferent arterial. Hopefully I spelled that right. My brain isn't working. We increase aldosterone secretion. And aldosterone um, increases the excretion of potassium, increases the reabsorption of sodium, and then we also increase the release of ADH. And ADH is an antidiuretic hormone, which makes it so that your pee is more concentrated. I had to like really think about that. Okay. Um, okay. So back to the glomerular filtration rate. So glomerular filtration rate is the rate at which everything is filtered, right? So each individual molecule or ion has its own filtration rate. And we can't really measure glomerular filtration rate directly because it's in the middle of a process, and how do you get yourself in there? You don't. So, um, instead, we came up with this idea of clearance. And clearance is something we can measure. So clearance When we measure clearance, we measure the amount of something in your urine versus the amount of something in your blood. So if a substance is completely reabsorbed, so you have none of that substance being excreted, the clearance value would be 0, right? Because you're not excreting anything. A good example of that would be glucose, because you don't excrete any glucose unless you're a diabetic, in which case you're a diabetic, so you do excrete glucose, but then we know you're diabetic. Um, so it's just basically like a ratio of stuff, an ion, in your plasma versus in your urine being excreted. And if something has a 1-to-1 ratio, then its clearance equals its glomerular filtration rate, right? So if a substance has the same clearance, or its clearance is 1, right? So it's like has the same amount in their blood plasma as in their urine, then that is what their glomerular filtration rate is. Okay, hold on. So I was wrong when I said that the glomerular filtration rate is different for every substance. It's not. Reabsorption is different for every substance. The glomerular filtration rate is the same all the time. Okay, just had to clear that. Anyways, um, so as scientists, we went about trying to find a molecule that had a clearance rate of 1. And we found one, and it is called inulin, not to be confused with insulin. Inulin is a type of sugar that so we have it in our blood. If we inject it into a person, it eventually will be completely filtered and then excreted. But we can find their glomerular filtration rate from it. Another one is creatinine. Um, and creatinine is naturally occurring in the body. So we know that everybody will have creatinine. It's always naturally occurring. So we don't have to do like this whole process where we monitor your urine for a long time while we wait for all the inulin to come out. We can just take your creatinine levels and find your glomerular filtration rate based on creatinine levels, because creatinine is excreted at the same exact amount that it is filtered, if that makes sense, right? So it's not reabsorbed at all in the body. There's no reabsorption, there's no secretion. It's just filtered and then excreted. That's it. Although, if somebody's supplementing creatine, then that can mess up the glomerular filtration rate. So sometimes that's kind of hard. But the idea with clearance is that we're comparing the amount of substance in somebody's blood plasma to the amount of the substance in their urine. Um, and if the substance is not reabsorbed or secreted at all in the kidneys, then that reveals the GFR. And creatinine is a very good example of that. Oof, so we use it in medicine all the time. So people measure urine creatinine levels. Um, okay. I'm like all over because I keep reading and then apparently not reading enough. Okay, so I'm gonna go back to this really fast and explain what happens at a cellular level with ADH, because I already explained aldosterone, but with ADH, we insert in the kidneys at the very end of this tube, we have what's called a collecting tubule. We insert aquaporins into the collecting tubule. Um, which then allows for urine to be concentrated. Because urine, by the time it's in the collecting tubule, is fairly dilute. It's like 60 millimoles per liter, whereas the outside of the tubule is much, much, much more concentrated. Um, And so if we had aquaporins, the water is going to move to the solute, but usually that membrane is not permeable to water. However, when we have ADH, we're basically telling our body, hey, we're dehydrated. Hey, we need to increase our blood pressure. For whatever reason, we need our blood pressure to increase. We need to increase our cardiac output, whatever. Um, so our body's like, hey, give me some more water in my blood. Like, let's figure this out. So we insert aquaporins and we remove water from our urine and put it back into our blood, therefore concentrating our urine. Okay, I swear, I'm gonna be more organized. My brain's all over. Okay. Okay, so I'm gonna do reabsorption probably a little bit unconventionally because I hate drawing the kidney cells. So, I'm gonna start with the proximal tubule and then just kind of go around, right? So if we have our nephron like this, and this is our proximal convoluted tubule and our proximal straight tubule and then our descending tubule and then like kind of our loop and then our ascending tubule and then our distal tubule and then our collecting duct is like somewhere in here, right? So I'm just going to go through each of these. Oh my goodness, I'm sorry. I'm going to go through each of these and um talk about what moves where, how it moves, um because I don't want to draw the cells because I'm opposed morally. So sodium is going to move out of the cell and into the bloodstream. Um, and this happens a variety of ways. So sodium is moved out of the cell by the sodium potassium pump. It works as a transporter for other proteins or like other things as well. So it helps to transport amino acids and like glucose against their concentration gradient. Um, it's transported with, oh, just a variety of things. So lots and lots of sodium movement here. Water is moved back to the bloodstream as well. So out of the kidney back to the bloodstream. And this is done through aquaporins and then another way called solvent drag. And basically this is the idea that as we're moving all of the solvents from the lumen um to the bloodstream, water's going to follow because water follows solutes. So it's just doing its thing. It's osmosis thing. And this is about 70% of these things move. So their TFP ratio at the end of the proximal tubule is still 1 to 1, or still 1. Okay. Glucose moves via to the bloodstream as well. So we move from the lumen to the bloodstream. I can't spell. And this moves via a protein transporter. And we have a pretty good amount of glucose transporters. These are not very easily saturated. So if you're saturating your glucose transporters and peeing out glucose, you probably are diabetic. Like I said earlier, I'm just going to say it all the time. Um, our amino acids are also going to our bloodstream from the lumen. Um, they also are moved through a protein transporter, and they are a little bit more easily saturated. This is 100% of these substances. They're like, after the proximal convoluted tubule, we don't have any more protein transports for these. So if you don't get them now, you're gonna excrete them. Period. We also are going to be using carbonic anhydrase in the lumen to put together molecules of hydrogen and bicarb, transport them into the cell as water or carbon dioxide, put them back in the blood where they'll dissociate. So we are going to be moving hydrogen into the lumen And we'll be moving CO2 mostly into the cell slash the bloodstream. Um, and then carbonic anhydrase, which I'm going to label as Ca because that's what we did in biochem, is going to come and make this equation work. I'm skipping the carbonic acid because I hate that step, and my chemistry teacher also hates that step, so sometimes I forget it exists, honestly. But it is in there, it just doesn't really happen in the body, so I sometimes ignore it. So yeah, that's kind of all that happens in the proximal tubule. We move a lot of water, a lot of sodium. All of our glucose, all of our amino acids are being moved back. We have a little bit of potassium movement because there are always potassium leak channels, so they're just going to be leaking with their concentration gradient as they should be. But the membrane really isn't permeable to chloride, so our chloride concentration is going to really increase. So the TFP of chloride will be greater than 1 at the end of this, whereas like the TFP of, wait, hold on. Yeah, it should be greater than 1. Where's the TFP of glucose? No, wait. Oh gosh, I would have to do the math. I need to like make a graph. But the chloride concentration will be much greater. It's moving at a way slower rate than water at this point because it's stuck in the cell, if that makes sense. Um, in this proximal tubule, the straight proximal tubule, we're moving alpha ketoglutarate, which is um a byproduct of the breakdown of amino acids, which then is going to play into our carbonic anhydrase reaction, and we're moving that. Um, I believe it's into the bloodstream. That's something I'm gonna have to go study. I'll just underline this because now I'm trying to remember. But again, carbonic anhydrase is gonna do this for us. Alpha ketoglutarate just goes into that. In the descending tubule, we are moving exclusively water. We're moving it via aquaporins into the bloodstream. I should keep this consistent. So we don't move anything except for water here. So the consequence of this is our urine becomes very concentrated. So we concentrate the urine here, which makes a lot of sense if you look at how the tubule works and how the nephron works through the loop of Henle, which I'm going to talk about in just a minute. Because the concentration of that actually increases, which is what allows us to move so much water out. Um, then in the ascending tubule, we move a lot of salt. So we move sodium and chloride into the bloodstream. And we do that via active transporters. I actually believe it might be secondary active transporters. But the membrane is not permeable to water at this point, so we're only moving salt, which will effectively dilute our urine. So by the end of this, our urine will be about 100 milliosmolar per liter, or 100 milliosmol per liter, 100 milliosmolar. The book says 60, Brother Hunt said 100 in the lecture. I'm gonna go with somewhere in between the two, or 100 because that's what he said in lecture. Not sure. Um, but yeah, so we're moving salt via active transport um across the membrane. And again, the idea of how the loop of Henle is structured makes this a lot easier and it makes a lot more sense. The collecting duct, there are two options. So we either can move nothing or we can move water out of the nephron, depending on ADH. So if in the presence of ADH, we move water to the bloodstream via aquaporins. If we don't have ADH, we're gonna do nothing, basically. That's pretty much, that's just what happens. In the presence of ANH, I think I read something in the book, maybe water moves into the cell or into the collecting duct, but I don't want to write that down because I'm not positive. But I know for sure that this is reality. So then the structure of a nephron is kind of interesting. So I'm gonna draw a nephron in a really different way. Hopefully, I can do this without making a whole ton of mistakes. But this is kind of tricky for me as of right now. Oh, my lines. So we're just gonna squeeze this one in at the bottom. Go with, just go with it. Okay, so right here we have an osmolarity of 300. In this gap, it's 400, 500. Hold on, I messed up. No, I didn't, it's fine. And then in this one, it's 600, right? Definitely did. I drew too many lines, but we'll just go with it. Just hear me out here. Okay, maybe pretend the last dotted line isn't there. Anyways, so we know that when blood enters the glomerular capsule, it has a osmolarity of 300 milliosmol, right? So if we draw a little picture, that's how many dots we would have. And then 400, we have some more, and then 500, and then 600, right? Huh, totally makes sense. So we have an osmolarity of 300. So when we enter our proximal tubule, we have an osmolarity of 300. And we know that we're permeable to water all the way down the descending tubule. And that's actually the only place in the nephron, the proximal tubule and the descending tubule. Place we're permeable to water all the time, right? So as we go down, the way that this is a cortical neuron, by the way. The way that this cortical neuron is set up is that it has, as we go down, the osmolarity increases. We get more concentrated as we go towards the bottom, which is what allows us to move more and more water out of the cell as we go towards the bottom, which allows us to concentrate our urine. So, water follows solute. We start at 300 here at the end of our proximal tubule. Then as we decrease, we're going to come to 400 because that's what the outside is. And then we come to 500 because that's what the outside is. Then we come to 600, right? And then as we ascend and we come back up, the active transporters on the ascending side have the ability to transport up to 200 milliosmoles different from what's on the outside, basically. So when we start at 600, we're going to actually transport to 400. And then at 500, we're going to transport to 300. Then at 400, we're going to transport to 200. And then at 300, we're going to transport to 100, right? And that's why we're able to get urine with an osmolarity of 100, a milliosmolarity, osmolarity, yeah, whatever, of 100 when the outside has a 300 milliosmol concentration because we're using active transport to shove out those solutes, to give those solutes back to the interstitial fluid, right? Um, then when we get over here, we have selective permeability if and only if we have the presence of ADH, right? So if we have ADH, then we insert these aquaporins using what we call principal cells, right? The principal cells are what have the aquaporins, and we literally just insert it into the collecting duct. And then as we go down, we're able to concentrate our urine back to 600 milliosmol because that's what it is down here, right? So we can concentrate our urine to be fairly concentrated. Now, what's really interesting is if you have a juxtamedullary neuron, you can elongate this so it's like it gets really long, and you can get up to 1200 milliosmolar concentration. So that would mean you can concentrate your urine twice as concentrated, which is why like some animals are way better at preserving water than we are because they can concentrate their urine way more than we can because they're cool and they have more juxtamedullary neurons than we do. Where we have like 90% cortical neurons, they have like 90% juxtamedullary neurons. For example, camels have lots of juxtamedullary neurons, so they can preserve water better than us. We're just not cool, so we have to pee all the time. But that's kind of like the idea of how that works. And with ADH, we insert, hold on, I gotta make sure that I'm actually explaining everything. Yeah, we insert aquaporins, right? And with more ADH, we can insert more aquaporins. And I'm assuming that the way that we get urine of different concentrations is we insert aquaporins further down, right? So the ones like down here would be inserted with more or would be inserted with more ADH. The ones up here would be inserted with less, which is how we get urine of different concentrations because we're excreting water from our nephron because this is the concentration outside and this is the concentration inside. Big difference. You know, we want to have water be happy and follow solutes, so it's going to go out of the cell instead of being in the cell. That's like the idea.